Good evening. Thank you all for coming. I work in the chemistry department here, as many of you know. I'm also a member of the local section, Wakarusa Valley local section of the American Chemical Society, the ACS. We have many members of that organization here. And also we have about 40 gathered here who are members of the Kansas College Chemistry Teachers Conference. So all three of those organizations have made this event possible. So thank you all. The lecturer, of course, is Dr. Eric Scerri, who's been around to meet many of you, and there's going to be another opportunity to meet him afterwards at a book signing. His two most recent books I have with me here on the podium. This one is The Periodic Table, Its Story and Its Significance. And this one, even more recent, is The Periodic Table, A Very Short Introduction. And both of these, and actually two other books, will be available in the book signing, and we'll have refreshments back there as well immediately after the seminar. I want to thank all those joining us today from outside the KU Department of Chemistry, especially if you have colleagues or classmates who, quite frankly, wondered what business you have attending a chemistry seminar. Part of Eric's success, I believe, is rooted in his ability to know when to ignore these disciplinary boundaries and combine tools that we might label in domains like history, design, and philosophy, for example. Eric received his undergraduate degree from London, CPGS from Cambridge, Master's from Southampton, and PhD from King's College London. This may be the first time I've ever had the privilege of introducing someone with advanced training in philosophy. I know for sure it's the first time that I've introduced someone who was born on the tiny island of Malta. And so this is the first time that I'm using the term Maltese to describe something other than a mysterious bird from American cinema. In contrast to the audience of that movie, our seminar audience today can rest assured that we have the authentic Eric Scerri here, who did eventually come to live on the California coast. For the past 12 years, he has taught general chemistry and other courses at UCLA, where his ideas have fueled a resurgence, if not a total new synthesis of the subject, philosophy of chemistry. Eric's very first publication was, as near as I can calculate, about 34 years ago. A short article simply titled, The Mass Space-Time Continuum. Like most academicians with enduring success, he's narrowed his topic in subsequent publications. And there have been, if you count his 7 full-length books, over 150 opportunities for him to help us make sense of this continuum that we're all a part of. Ladies and gentlemen, The Mysteries of the Periodic Table from Dr. Eric Scerri.
Well, thank you very much, Roderick. Can you hear me? Is the mic on? Doesn't sound like it. I thought I saw a little red light. There is a red light. Someone has to adjust something. What can you do? Philosophy theoretician. I can't even work a microphone. You know, I use one of these almost every day to teach. So, I was saying, thanks very much for that very nice introduction, Roderick, and thank you for all the arrangements and your attention to detail, and it's been great. I've enjoyed my time here. I'm here again tomorrow. I'll be giving another lecture in the conference, and it's wonderful to see so many people come out for the icon of chemistry, the periodic table. Of course, it's not just chemists who love the periodic table, but it belongs to chemists, really. Where to start talking about the periodic table? Well, I'm going to start where it all started, in a sense, which is Mendeleev. This is a moment in the life of the family Mendeleev and the translation of the Russians. Someday, maybe we can understand why Dmitri always organizes his blocks in the same way. So I guess that's where it really started. Much has been written on the periodic table, and this is just one brief quotation to show the importance of the periodic table. The periodicity of the elements is the most important coordinating principle known in physico-chemical science. it may aptly be described as constituting the cornerstone of modern atomic physics, right? Quite apart from being the cornerstone of chemistry. There is a sense in which, and I'll be getting onto that, it is the cornerstone even of atomic physics. Now, the periodic table in recent years has become something of a cultural icon. And it's not just chemists, it's not just physicists, it's not just biologists, it's artists have helped themselves to the periodic table. And I've given entire lectures on art inspired by the periodic table. Here's just one. Actually, I'm going to show one or two. So it's a design icon. Here is the periodic table of printmaking. And I'm sure you've seen many, many of these. Here is the periodic table locker room, something like that, where the rare earths have sort of gone around the corner. Here is a door, which has a little piece of the periodic table. It was actually a door of a restaurant in London, and it was auctioned for some absurd sum of money, which made Damien Hirst even richer than he already is. There's another one, fairly recognizable, you know, with the elements if you look hard enough. There have been two recent excellent books on the periodic table and the elements of the periodic table. So there's been quite a surge in popularity in the periodic table and the elements. I don't think there's been anything like it. It's nice to see chemistry finally coming back at physics and biology. In the past, it was always physics that would get the action. You know, all the TV shows would always be about physics, astrophysics, black holes, cosmology, expanding universe, what have you. And of course, life and biology gets a lot of attention. And chemistry somehow squeezed in the middle. You know, you go into your local bookstore, if there are any bookstores left, which, and you look for chemistry, and you're lucky if you find 4 or 5 books, usually in the wrong section anyway. It's beginning to change. Beginning to change. Advertisers have helped themselves to the periodic table. This is J. Crew, I think, that used this. Unfortunately, they get the chemistry wrong, but at least helium in the same group as phosphorus is going a little bit far. And not to mention tungsten and zinc and silver, I think it is. So it's all wrong, but it's getting there. At least they've woken up to the periodic table. And this is one of my favorites, the periodic table of guitarists. And if you are a guitarist, and I am actually, you really like this, because you can click in, and there's 200 in this periodic table. And you can sample their music and watch videos of them and find out where their next gig is and all kinds of wonderful things. And then there are something like, literally, over 1,000 periodic tables that have been published. Some on the internet. The internet has, you know, made this something of an explosion now, but even in print, there's something like 850 to 900 periodic tables. And they're coming out all the time. Right? People love to devise new periodic tables with some variation, sometimes a small variation, but sometimes claiming that this is a really profound variation. So just as there are people trying to write new theories of relativity all the time, there are people trying to devise new periodic tables all the time. This is the inverted coat hanger periodic table, which ends very definitively with uranium at 92, nothing beyond uranium. This is actually a version, an updated version of a Mendeleev table of 1870. Then there are these pyramidal tables. Niels Bohr, the physicists, favored this kind of a periodic table. Although this one you can see is much older, you know, if you can see the date at the bottom, 1882. But it's been updated again to include some modern elements. All kinds of spiral periodic tables. And of course, a spiral is a really good idea in the periodic table because that's what it's all about. It's like a clock face. You know, the big hand comes around and gets to the 12 again. That's periodicity. Which member of the audience has never heard of the periodic table? Okay. Then there are these ribbon or zigzag periodic tables. And again, you know, I could give an entire lecture on the variations. There's another one. This is Crookes, William Crookes, a London chemist and inventor. He was actually the editor of Chemical News magazine, the equivalent of Nature magazine at the time. Now, if you look on YouTube, just on YouTube, right, you will find, or I found the other day, 241,000 hits on periodic table videos. Right? If you look at periodic table, 22.8 million. It's even more than quantum theory. It's even more than relativity theory. That's surprising. And of course, there are no end of variations of the Tom Lehrer song done by Tom Lehrer himself, by 2-year-old children. You name it, it's there. Okay, now, of course, the periodic table is the workhorse of chemistry. It's, as I said already, the cornerstone of chemistry. It's the paradigm of chemistry. All of chemistry can be hung around the periodic table. As such, it serves a tremendous purpose. And not just chemistry. You know, as I was saying before, physicists will have it hanging on the walls of their labs regularly, and biologists and geologists and so on. So it's what's been called the paradigm. It's an example of a paradigm, meaning a framework, an overarching framework. And I'm sure you've seen diagrams like this, which use the periodic table in order to display information, be it atomic size, electronegativity, hundreds and hundreds of properties. And at a glance, you can see how it's varying across the elements, down groups. The periodic table is still vital, in the sense of it's still highly relevant. It's not just some relic that hangs on the wall of the lab or in the back of the textbook in case you would occasionally want to look up an atomic weight. Right? It serves a purpose. It continues to. Here's a very simple example. In 1986, high-temperature superconductivity was discovered. And it was discovered, and this is the property of superconducting at a relatively high temperature. It turned out it was 30 K when it was first discovered. Before then, high temperature superconductivity was taking place at extremely low temperatures, 3 or 4 K, which is difficult and expensive to produce. So they found that it could be done with this lanthanum barium copper oxide compound. Okay, that's pretty good because it's gone up to 30. Could it be any better than this? And it could. And the way they did it was to quite simply look at the periodic table and to reason that if lanthanum is good, maybe elements in the same group in the periodic table could do as well, if not better. And sure enough, when they substituted the yttrium for lanthanum, the high temperature superconductivity shot up to 90 degrees K. So I put this up as an example of the continuing importance of the periodic table. And you know, there's no computation and high-level theory that's gone into this. It's just looking on the periodic table and arguing by analogy. Then there's it's still vital in this sense, and I'll be taking up some of these issues. It's still relevant, still debated as to the placement of several elements. You may be surprised to hear this, but different periodic tables put hydrogen in different places. Helium occurs in different places, and so do some of these elements. Now, today, for those of you who are at the conference, in your conference pack, we were given 3 periodic tables by various publishers. And guess what? All 3 periodic tables were different. Right? They were different, especially with regards to group 3 of the periodic table. And I'll be coming back to that and looking at the different possibilities facing the group 3 elements. Okay. Now, I know you all know what the periodic table is, but just bear with me for a moment as I go through this anyway. What is chemical periodicity? Well, the simplest way I found of explaining it is to say that if you put the elements in an ordered sequence, right? I've done it up to 24 here. Every now and then, you arrive at an element which is similar. So you move along that sequence, and say you pick on this one, and then you move along this sequence and you arrive at neon, which is somewhat similar to helium, and then you move along another sequence and you arrive at argon. That is the essence of periodicity. It's as simple as that. It's very, very, very simple. Right? You move along, and every now and then you get a repetition. Now, 2 little complications. First of all, it's not a repetition in the strict sense of periodicity, because you're not coming to exactly the same point. you have an element which is similar, not exactly the same. So it's an approximate repetition. Second point is that that repetition occurs after a different length, or rather, it's 2 elements, and then 8 elements, and then another 8 elements, and then 18 and 18, and so on. And the period length is varying. So what you do when you chop that up, and you take, say you had this as a strip of paper, and I took a pair of scissors and cut it here, and I cut it there, and I cut it there, and so on, according to the colors, then you just paste one above the other, and you've got the rudimentary periodic table. Right? That's all there is to the periodic table in a sense. Okay, now of course, this isn't going to get you very far because, as you probably know, the next element is not, in fact, a noble gas. Right? Iron is not a noble gas. So what happens here? Well, it's the fact that the period length is starting to get longer and longer. And so now if I look at all the elements, all the way to copernicium, the most recently named element, 112, now I have to make my cuts. Well, the cuts at the beginning are the same, and then the cuts get further and further apart, and then now use these pieces of paper and paste them one above the other, and I get the familiar periodic table. Okay, so now a little bit about the history. Where did all this come from? Where did this very simple and powerful idea develop? Well, one useful starting point, although I could go further back, is John Dalton, a Manchester school teacher, who, as you know, revived atomic theory, made atomic theory quantitative. The idea goes all the way back to the Greek philosophers. But the Greek philosophers just thought about atoms and didn't do anything very serious with it. John Dalton set about estimating relative weights of different atoms, and he produced, here's one of his earliest tables of atomic weights. It even contains a number of molecules. You look at the value for oxygen, it's a little surprising. The data he was working with was inaccurate. He then modified this to be 8, and then it was realized that it wasn't 8, it was in fact 16, because of the formula of water. Well, it's a long story. Now, this was essential, because the sequence I just showed you a moment ago, where I put them all in a line, was essentially a sequence of increasing atomic weight. So this really is the first important step, knowing the weights, having some way of ordering them at least in a one-dimensional sequence. The second dimension yet to be discussed. There were then 2 ideas that really gave the periodic table some shape. The 2 ideas being triads and Prout's hypothesis. Let me take triads first. Triads were discovered by Dobereiner, a German chemist around 1827. He noticed there were groups of 3 elements which had remarkable properties. Here's one of those groups. You'll probably be familiar with this. Lithium, sodium, and potassium have the property that one of those 3, sodium, has the atomic weight which is approximately the average of the other 2. So if you add 7 to 39 and divide by 2, you get 23, round numbers. That's already interesting. But the equally interesting thing is the fact that that middle element has chemical properties intermediate between lithium and potassium. Right, so here is the first hint that there is some numerical regularity that is now connecting elements. It's one thing to have isolated atomic weights of things, but this is a relationship that somehow suggests that there's a deep relationship between certain elements. And various triads were discovered, and little else was done. People went about looking for more and more triads. Sometimes they went a bit too far and thought they discovered triads where they weren't really there. Here are 4 of Dobereiner's triads. You can see they're fairly accurate. The actual weight of bromine is 79.9, whereas if you take the average of these 2, it's closer to 81. It's not too bad. Similarly, this one is quite good. Here's the calcium, strontium, barium, and again, quite good, but not exact. Right? Not exact. So some people doubted this. Some people thought this was just a coincidence, or numerology of some kind. Now, if you now move to atomic number, which is you probably know, is the correct ordering principle rather than atomic weight. And then you try the same thing with atomic number, you find that triads are not only correct, but they're exactly correct. Because once we go to atomic number, these are whole numbers anyway. So in the chlorine, bromine, iodine triad, 35 is not only the atomic weight, the atomic number of bromine, it is the mean of those two numbers. Right? So triads have, if anything, got stronger over the years. They're now exact. Here are some triads superimposed onto a long-form periodic table. This is, in a sense, more correct than the usual periodic table, which, as you know, detaches the rare earths and leaves them dangling at the bottom in a disconnected sort of footnote fashion, as if they were unimportant. And of course, we're learning these days more and more just how important those elements are. Commercially, they're extremely, extremely important. Okay, so their rightful place is to open up the periodic table between the S block and the D block and to put these in. Okay. Now, that's just a detail, because what I'm looking at here are some triads. Okay, so here's the helium-neon-argon triad, using atomic numbers now. Here's another triad. Now, just as much as this triad is perfect, so is the one next to it. So is this one, so is that one, so is that one, so is that one. Okay. Now, what is this mysterious triad property? Like I promised you mysteries of the periodic table. Well, actually, this one is not all that mysterious, because if you think about it, let's say I select sulfur, and now ask the question, how far do I need to move along in the sequence of elements to get an element that's like sulfur? And the answer is 18 elements. I have to go chlorine, argon, all the way there until I arrive at selenium. That happens to be 18 elements. Now, how many elements must I advance through to go to another element that's like this and this? The answer is another 18. And so it's hardly surprising that selenium lies right in the middle, right, between sulfur and tellurium. There is no mystery in triads. They follow naturally from the fact period lengths repeat, or at least some period lengths repeat. So all you have to have for a perfect triad is you have to have one element in a shorter period and two subsequent elements in periods of the same length. So it's not going to work with selenium, tellurium, and polonium because you don't have that. But it is going to work with the next one down. So it works, it doesn't work. It works, it doesn't work. Right? The other main guiding principle that led to the periodic table was invented by Prout, a Scottish physician, a doctor, working also in London. And Prout did something that, in a way, was quite simple. He looked at the atomic weights of the elements, the then-known atomic weights. Again, some of these may be a little unfamiliar because we have different values now. I mean, sodium is no longer 93.3. But what he noticed was that a number of them, a large number of them, were multiples, whole number multiples of hydrogen. Can I get a cup of water? I'm fighting a sore throat. Okay, so now, if a number of them are whole number multiples, the natural conclusion is to think maybe all the elements are literally made of hydrogen. Right? And that's Prout's hypothesis. The elements are multiples or composites of hydrogen. Okay, so now the opponents of Prout said, but wait a minute, what about this, what about that, what about that, what about that? And the defenders of Prout could just say, well, you know, it'll come out okay in the end. It might be that they've been measured not so accurately. So Prout's hypothesis fell into some disrepute, right? Because it's just not exact enough. There are too many exceptions. And even though people tried to remeasure atomic weights, it didn't solve the problem. It didn't help the situation. There were still too many stubborn exceptions. Now, Mendeleev, the discoverer of the periodic system, or at least one of them, interestingly disliked both of these ideas, or he claimed he did anyway. Let's take Prout first. He definitely disapproved of Prout's hypothesis, because for Mendeleev, the elements were strictly individual. They all had their own characteristics. He did not like the idea of reducing everything to one primary matter, or one basic form of stuff, hydrogen, for instance. So he was dead against that, and there are a number of passages where he says, flat out, I don't like this. On the question of triads, he claimed he didn't like triads, but funnily enough, he used triads himself, And in fact, he used them with a vengeance, because he used it this way and that way. So for instance, in his textbook, he says, if you want to calculate the weight of selenium, which was known, so he could check his method, what do? Well, you take this plus that plus that plus that, and you divide by 4. And you can see you get a good approximation. So in fact, he didn't realize he was using triads in 2 directions. Now, Proud's hypothesis, of course, makes a return in a modified sense, right? Atoms are composites of hydrogen in the sense of protons. Neutrons don't do too much chemically anyway. Of course, they're relevant, of course, isotope studies and so on. Astrophysically, we're told by the astrophysicists that the elements were literally formed from hydrogen. Right? 2 hydrogens get together in the Big Bang and form, shortly after the Big Bang, and form helium. And then, at least in principle, 2 heliums get together to form beryllium and all sorts of complicated mechanisms. So, yes, Proud was right. And a bit later on, if I get to it, I will be suggesting that triads can make yet another form of comeback. But let's see if we get to that. Coming back to the historical sequence, there were a number of issues surrounding atomic weight. There were competing atomic weight schemes, and lots of discussions. And this, as you may know, was resolved by Cannizzaro, drawing on Avogadro's hypothesis. Complicated issue, no time to do it now. So let me just, after showing you this stamp all in Italian, move on. Okay, so what Cannizzaro did was he standardized atomic weights. And this is what really opened the door for the discovery of the periodic system. Now you had atomic weights, you had the idea of triads, you had Proud's hypothesis, which was also contributing. And by the way, people wanting to check Proud's hypothesis or the idea of triads were busy measuring atomic weights ever more accurately, and therefore contributing to the growth of the periodic system. Once Cannizzaro had published his more accurate, rationalized set of atomic weights, it was just a matter of time. And it took about 7 or 8 years, but in different countries, at about the same time, the periodic table was independently discovered by at least 6 people. The first discoverer of chemical periodicity, in the sense that after a certain number of elements you have a repetition, is this man, Bégayer de Champ-Courtois, a Frenchman. And his periodic table, interestingly, is a 3-dimensional system, in the sense that he has all the elements arranged in a line, and then he wraps that line around a metal cylinder, and here it is in the actual model preserved in a museum somewhere. And then the point really is that if you look down a vertical column, you have elements that are similar: lithium, sodium, potassium, magnesium, calcium. This is a little wrong. This needs to be pushed over, of course. This is the world's first periodic system. A good 7 years, I think, if I remember correctly, before Mendeleev. He had very little recognition. He happened to be a geologist, and chemists didn't really look very much in the geological literature. And to make it worse, the publisher lost the diagrams, and the paper was published without the diagram. And of course, it's all about the diagram when we're talking about periodic. Perhaps the second was a London chemist, an industrial chemist, Newlands, and you probably know the story of Newlands. Newlands announced what he called the law of octaves. He made the obvious analogy with a musical scale, that after 8 notes you come back to the same notes. He was laughed out of court. People thought this was ridiculous, and people thought he was making a serious analogy between somehow music and the elements. And so, you know, the British public being what it is, or the British intelligentsia being what it is, they just killed this idea off, and he spent the rest of his life trying to get a little bit of recognition for this discovery. He had rediscovered the periodic system. Gustav Heinrichs, a Danish polymath, came to the United States at an early age. He was a political refugee from Denmark. He published this rather elegant periodic system. You know, like the spokes in a wheel. And you can see the familiar grouping: fluorine, chlorine, bromine, iodine, nitrogen, phosphorus, arsenic, antimony, bismuth, and so on. In fact, here's an interesting one, because copper, silver, and gold, even Mendeleev did not have that in his initial periodic tables. So this guy was ahead of Mendeleev, literally ahead of him by 5 years, but even chemically was more correct. This one hardly ever gets any credit. This is another one, William Odling. He always reminds me of a certain actor. Robin Williams, yeah. Anyway, so Robin Williams devised this periodic system. So again, perfectly respectable periodic table for the time, showing a lot of the familiar groupings, nitrogen, phosphorus, arsenic, antimony. One interesting thing about this was that they're all arranged according to increasing atomic number, except for a couple of places, one of them being tellurium and iodine, where if you arrange them according to increasing atomic weight, it's wrong. Iodine should go into this group, tellurium should go into this group. And so Odling was forced to reverse them. It's a pair reversal. Mendeleev usually gets all the credit for that. And again, it was done before by this man Odling. We're coming ever closer to Mendeleev. His closest competitor was Lothar Meyer. Lothar Meyer published this famous diagram of atomic volume against atomic weight, and showing quite clearly that after a certain interval there is a repetition, seen especially with the alkali metals. Right? Now periodicity is just jumping out at you. If you didn't believe it before, now you've got to believe it. Right? That there's a recurrence. And then comes Mendeleev, who gets almost all the credit. There's much debate as to whether he gets maybe a little too much of credit. Okay, let me go into that briefly. Here is one table, not his first, but one of his most successful tables. It's an 8-column table, and the 8th group is a sort of dumping ground, because he didn't know what to do with these elements, and so he just dumped them into group 8. This is not, this is not the noble gases. The noble gases haven't been discovered yet. The noble gases are about 30, 40 years down the line. And of course, he leaves spaces, famously, and not only leaves spaces, but predicts the atomic weights of these missing elements. And even more remarkably, the elements come out to have almost exactly the properties he predicts. For instance, he predicted an element, Eka silicon, one like silicon. It was discovered, it was eventually called germanium. It was discovered 15 years later, and if you look at the properties, they're almost exactly what he predicted. It's almost as if Mendeleev can tell the future. Right? But he hasn't got the stuff. It's 15 years before you can get hold of the stuff, and he knows somehow. Now, again, this is not so mysterious, because he was doing some interpolation. If you draw a smooth curve through many of these properties, you can make a good guess at what the properties will be. And that's what he was doing. Now, this gets a little overhyped in the textbooks about just how successful Mendeleev was at making these predictions. So without trying to take any credit away from him, or maybe just a little, right, I want to go into the issue of, well, okay, prediction as opposed to retrodiction. What's more important for the acceptance of a scientific theory? We usually think it's prediction, because if a scientist predicts something and it turns out to be correct, then there is a sense in which the scientist knows the future, knows the inner secrets and mysteries of nature, right? They've really captured something. How would they know the answer if it hasn't yet been discovered? It's, psychologically, it is definitely an indication of a good theory. Whereas accommodation or retrodiction, you can always argue that somehow the scientists knew what they were driving at, and therefore they could fudge their theory to make it come out right. It's like the student who can't do the problem looks at the answer in the back of the book, and then they can do the problem. That's usually considered not quite as good as doing it without looking at the answer. So which is more important of those two skills in a scientific theory? Well, you'd be surprised to hear that philosophers, historians and philosophers have been arguing about this for more than 100 years. Because although the traditional view is that prediction gets all the credit, there is a case to be made for accommodation. And that sometimes maybe successfully accommodating already known facts is more impressive. For one thing, with already known facts, the data is stable. It's been measured many, many times. Whereas with prediction, often the prediction is made, somebody makes an observation, and it's heralded as a new discovery or a confirmation of the theory. But then it turns out, well, that observation wasn't much good. We don't have that problem with accommodation. What about Mendeleev? If we're going to give him the credit for predictions, how well did his predictions actually fare? He made a total of 18 predictions. Only 9 of them were found. That's 50% success rate. That's very unimpressive. That's as, you know, astrologers can do that. We're supposed to be a little better than that in science. So if it really was down to predictions, we should point out that actually he got it wrong half the time. So why give him the credit for predictions? When the Davy Award was made, and that was the equivalent of the Nobel Prize at the time, I'm talking about 1880 something, it was given not just to Mendeleev, but to Mendeleev and Lothar Meyer. And as is well known, Lothar Meyer didn't make any predictions. So at least the people making this award believed that accommodating already known elements was just as important and just as difficult. But it's no easy thing to accommodate all the elements. You haven't got the latitude that you want. Right? You've got to get it right in 2 directions. And of course, Mendeleev did a whole bunch of other things. Okay, moving on historically, William Ramsay discovered a very strange element, argon, which had an atomic weight of 40 and had no place in the periodic table. I'll show you why in a moment. There was a dispute as to whether it was monoatomic or diatomic. Most gases, of course, are diatomic. There have been no monoatomic gases discovered. Completely unreactive, so much so that people thought, well, it doesn't even belong in the periodic table. Right? The periodic table is supposed to be about elements that react. And various other. And just to make this even more of a conspiracy to confound people, it's one of those rare examples of pair reversals. So the atomic weight was really deceiving people. Now, here's the periodic table that was available at the time. If you look, 40 would put it, well, would it put it here? Would it put it here? There is an element of 40. Where are you going to put it? As you probably know, it actually gets placed eventually after chlorine. Okay? But on this table, you would never dream to put it there. Besides, it's not like these elements. Right? So for 5-6 years, nobody knew the answer. Mendeleev tried various things. At one point, he thought it was triatomic nitrogen or something. All sorts of attempts. Then a whole bunch of others were discovered, and now the problem became really serious, to the point that people said, well, that's it, the periodic table has had it. We're going to have to discard the periodic table because it cannot accommodate these 5 or 6 elements. But then Ramsay himself came to the rescue, and it became clear that all you had to do was to add a separate column on the right. Of course, I'm using an updated periodic table here. But essentially, you put a column of elements to the right of the halogens, and everything's fine. Right? Nobody had predicted any of these elements. Right? Again, it's to be taken into consideration when thinking about the role of prediction. Then physics begins to invade the periodic system. So you have such things as J.J. Thomson discovering the electron, and it becomes clear that the atoms are not indivisible. They have at least one kind of particle that comes out of them, if you like. The experiments on radioactivity begin to happen, where it becomes clear that the elements are not even unchangeable. Elements can change into other elements, and in doing so, they break off certain particles. By the way, Mendeleev would have nothing to do with it. He was still living at the time, right? And he, in fact, visited the Curies, and he walked away saying, I don't believe any of it. He could not accept that there were particles smaller than atoms, or that the elements could change into other elements. And Rutherford discovers the structure of the atom, or begins to discover the structure of the atom, and so on. And in fact, quite quickly, the physicists became really quite sort of condescending towards chemists, and made statements like this. And in other places, Rutherford said, all science is either physics, or stamp collecting, or chemistry. Right? So for him, stamp collecting and chemistry were synonymous. And as you know, Rutherford got the Nobel Prize. Chemistry, a bit of an embarrassment for him. Moseley essentially discovered atomic number, and now it became clear why those pair reversals had been so mysterious. For instance, tellurium and iodine, as you know, if you look at atomic number, then tellurium should correctly come before and this is because of the isotopic makeup of those two elements. Everything becomes clear overnight almost after Moseley made this discovery. And there are four of them, only four of them, right? There's one, two, those two were known at the time. This one is the one involving argon, and this one would not have been a problem for the early discoverers because protactinium was only first discovered in 1917. G.N. Lewis could be credited with the world's first electronic configurations. But they were rather odd configurations. He made this famous sketch, which has been reproduced many, many times, in which he thought that the electrons were on the corners of cubes. Right? Not a nonsensical idea, because, of course, the number 8 is crucial to the periodic table. Right? The periodic table is essentially a repetition after 8. I know that there are transition metals, but the fact remains that if you think of S and P, it does always fill a shell when you get to 8. So he wasn't that far off. Of course, he got it wrong because he thought they were static electrons on the corner of cubes. But he's the first to suggest that the reason why beryllium and magnesium are similar is because you've got 2 electrons on the corner of its cubes, and boron and aluminum are similar because you've got 3 electrons and so on. That's essentially the idea. Thomson, in the meantime, suggested that giving an explanation for the periodic table was the problem for physics, and he set about trying to do that himself. And he did this by drawing an analogy between some experiments that had been conducted in the United States by Alfred Meyer. Meyer took some corks, he put steel needles in the corks, he arranged this in a bath of water, he had an electromagnet. And the strange thing that happens is that these corks take up circular arrangements. If you have 4, you get 1 circle. If you have 5, it's still 1 ring. But once you start to go to 6 and higher, they form more and more rings. And it occurred to Thomson, and nobody's really sort of worked out why he had this idea, that the electrons in the atom, remember he was thinking of the electrons as being embedded in the atom, that they might take up circular arrangements, and he came up with this set of configurations. So this is the first time a physicist came up with configurations. And he argued that the reason, so you've got 5 in a ring, and then 2 rings, 1 electron, 5 electrons, and so on. And then you get to a point where there are 3 rings. And he said, well, the reason why this element might be similar to this element is because they have analogous configurations. And this element might be similar to that element because they have analogous configurations. Okay? Which is the idea we still work with. Of course, he got it wrong because element 5, boron, is nothing like sulfur, and carbon is nothing like chlorine. But he wasn't to know because at the time it was not clear how many electrons each atom actually had. Then physicists started to get serious. Right? Quantum theory came in, and then Bohr produced a more successful set of configurations. Here is Bohr's configurations based on just 1 quantum number. Right? So this is the idea, which is still used in teaching chemistry, of course. We mentioned this at the conference today. You know, shells with a certain number of electrons. It gets you quite far to this day. Then a second quantum number was discovered by Sommerfeld, and Bohr used it to get a more refined, more detailed set of configurations. And then a third quantum number was discovered by Stoner in England, and Bohr capitalized on that and got another set of configurations. And then Pauli discovered the 4th quantum number, and then you end up combining the 4 quantum numbers, and you get this familiar thing that all students are dragged through. Right? So that you can predict the number of electrons that can go into any shell. And it's a pure consequence. And this is really wonderful. I mean, this is purely theoretical. On the basis of the hydrogen atom, right, and what it does and what its quantum numbers are, you hypothesize that it will apply to other atoms. You combine the quantum numbers, and sure enough, because of when the first quantum number is 1, that can only be 0, that can only be 0, this can be a half up. So 2 electrons in the first shell, 8 electrons in the next, 18 in the next. Now, if you do a running total on these, you get 2, 10, 28, which means that if you were to try and predict the periodic table on this basis, you would get it wrong. What I've just been going through is the closing of the shells, 2, 8, 2, 10, 20, this is running totals, right? 60, 110, but of course this is not where the periods close. The periods close at these numbers. another mystery. But again, it's not a mystery. The reason why these two don't coincide is because of the period doubling. It's because the shells don't fill sequentially. It's not a question of filling first shell, then second. Well, actually, it is first, then second. But then the trouble starts. The third shell doesn't completely fill before you start to fill the fourth shell. Okay? Now, here again, I'm just emphasizing the first period is 2, then 8, then 8, then 18, then 18. Now, it turns out, rather surprisingly maybe, that even quantum mechanics, even when taken a bit further by Heisenberg and Schrödinger, and by now the physicists are getting completely outrageous, right? Now physics is capable of eating chemistry with a spoon, right? Well, they haven't quite eaten chemistry with a spoon because this simple n+L rule, which does govern the order of shell filling, to this day has not been derived by quantum physics. Okay? And there have been many attempts, and it hasn't been done. Doesn't mean it can't be done, right? Doesn't mean that maybe people are not trying hard enough, but it's yet to be done. So chemistry is not fully reduced to physics. Chemistry is not nothing but physics, although physics has produced a tremendous advance on understanding the periodic table. Then there are the 20 or so anomalous configurations. They have not been explained from first principles. They can be accounted for, but not theoretically starting just from theory. And if physics claims to eat chemistry with a spoon, that's what it should be capable of doing, deriving everything. Then there's the threat from relativistic effects. You may know that with relativity theory, when you get to these high Z numbers, the elements start to misbehave a little bit. And the worry has been that is there a point at which the elements don't behave as they should do according to the periodic table? Right? And in fact, it began to look like this was happening because on the early studies involving Rutherfordium and Dubnium, these elements here and here, they did not behave like zirconium and hafnium and niobium and tantalum. They did things that they shouldn't be doing. In fact, for instance, Rutherfordium behaved more like plutonium, which is really quite far away in the periodic table. And dubnium also misbehaved. So then people started saying, well, now the periodic table has met its match, and now the periodic table is done. But actually, the odd thing was that when they got to element 107, borium, difficult to work with this, of course, it's very, very short-lived, but there is an isotope that lasts a massive 17 seconds. You can make compounds of it, and the compounds have the required formula that you would expect from that group. That gives you at least some support for the fact that if there are compounds that are like technetium and rhenium, the elements above it is the periodic table. The article that appeared in Nature magazine was boring borium, because it was doing what it should do. Right? So to some people this was boring, there's nothing novel there. You can do better than that though, because if you measure the volatilities of those three compounds and ask, is this element really in this group, then you can apply the principle of triads, once again, to the compounds now, and you can compare the actual value of the volatility of this compound with the value you would predict from just extrapolating. In this case, it's extrapolating, because we know that value, we're trying to predict that value, and then we check it with the experiments. And you can see there's an error of about 7%. That's not bad. Okay? So this element really does belong in that group. Right? The periodic table is safe up to 107. Position of hydrogen is much debated. How am I doing with time? I've still got 10 minutes officially, but all right. But is it okay to go on a little?
Let's go for it.
Oh, let's go. Position of hydrogen. Now, I'm sure you're aware of this. Position of hydrogen, there are many places you can put hydrogen. Here are just some of them. Most people, most tables, of course, put it there. Some tables put it here. Some people, well, this is an even odder one, but some people put it in the carbon group. Why? Because it's got a half-filled shell. 1 electron out of 2 possible electrons in hydrogen. Compare it with carbon, which is 4 out of 8. I mean, I think that's a terrible argument, but it's been published in JChem Ed, an article by Michael Cronin, and he's convinced it's This particular version is because of the electronegativity, which is just so but that's even crazier because you're not putting it into any group. And then there are people who can't make up their minds as to whether it's group 1 or group 17, and they just let it float. My friend Atkins likes to do that. Peter Atkins, in most of his tables, floats it. Now, that's a little bit like saying that hydrogen is above the law. The law is the periodic law. Every element should conform to the law. But as you know, in Britain, there are some individuals that are above the law, like the royalty don't pay taxes. Did you know the royalty doesn't pay tax? So that's the way Atkins is figuring this out. So I've talked a bit about hydrogen. What about helium? There's a question about the placement of helium, and there are questions about these which I'll come on to. Of course, this raises the philosophical question of, is there an optimal table? Why should people like myself and Atkins and others even be asking this question? Is it just a matter of convention where you put hydrogen? Well, I believe that it is, one can ask this question. I believe that there is a matter of fact about the issue. In other words, hydrogen either belongs in group 1 or it belongs in group 17. It's not our decision to put it here or there. We may not know the answer yet, so I'm arguing that there is an actual answer to this question. There is a fact of the matter. Not everybody shares this view. A lot of people say, well, it's just convention. Like, why are you even worried about this? What hangs on it? So here's one way to attack this problem. You go back to the idea of triads of elements, and now consider atomic number triads, and you can try and maximize the number of atomic number triads to get even more than there are at the moment. Now, at the moment, hydrogen is stuck there. It's not a member of a triad. Right? 1 plus 11 divided by 2 is not 3. But notice that if you were to take hydrogen and bring it here, as I do on this, or before that, here are all the triads. I had a student doing this. I have no idea how to do this on PowerPoint or whatever it is, but here are all the triads, right? So we take hydrogen, and we move hydrogen to there, and we arrive at this. We have a perfect triad. Right? That is a further argument for moving hydrogen to that position, because we've got yet another triad. So whereas had it stayed there, it would not have been. Now, you may say, well, so what? We need a bit more than that. And this is a debate that's been going on in the literature for some time. I'm not claiming it's a knockdown argument, but it's yet another argument, quite apart from the chemical arguments such as hydrogen is a diatomic gas, as is fluorine, as is chlorine. But you can be deceived by that because, of course, here, oxygen's a gas, but sulfur's immediately a solid, so you can't be sure about physical states of elements. That's never been a definite criterion about the periodic table. So in my periodic table, I go from there, and now people like to have hydrogen in the top left-hand corner. So if you want hydrogen in the top left-hand corner, I will slice the periodic table there, and I'll give it to you like that. Okay? Now, a nice little bonus of this is that I now have 8, 8, 18, 18, 32, 32 if this is incorporated. So that other little anomaly where there was only one period with 2 elements is taken care of. People worry about this because you lose the familiar trends, right? The atomic radius doesn't decrease. So if you don't like that, I'm quite happy to go back to that. On that, I'm not going to lose any sleep over it, one way or the other. I'm interested in placement, I'm not interested in shape. Many other people have, of course, put hydrogen in the halogens. Here's someone back in 1884. In fact, I've counted about 30 published tables that have done it. I did it in 2008, but I think so far I'm the only person to do it on the basis of triads. What about helium? Helium is actually debatable, because helium's got 2 electrons. Why not put it in group 2? 2 outer electrons. I mean, if chemistry is nothing but physics and electronic configurations, then it really does belong there. And many physicists feel that it should be there. So on one hand, it points to group 2. On the other hand, the fact that it has a full shell makes us want to place it where we usually place it, which is in group 18. Which is it? Right? Assuming there's a fact of the matter. Okay, so what about, now what's happened here? Well, here is where we take helium from there, and we put it there because of its 2 outer electrons. And now, having done that, some people like to slice that just there and put the S block here. Right? It's called the left step periodic table. And they end up with this very pleasing shape, which again has the nice property of having 2, 2, 8, 8, 8, and so on. So this has attracted a lot of attention, a lot of debate. There's only one problem. Chemists don't like it, because you know, however much you argue it, helium is not an alkaline earth. Right? So this probably is not going to fly. But you'll be surprised at the amount of argument that's gone over this periodic table. Okay, what about group 3? Now the weird thing about group 3 is that you see some periodic tables which have, well, let me show you what I mean. Here's the more traditional version. Group 3, meaning this group. Unfortunately, I have the old numbers here. You know what I mean. Scandium, yttrium, lanthanum, and actinium. Some periodic tables, I haven't counted, I haven't done a statistical analysis, you'll find scandium, yttrium, lutetium, lawrencium. Right? In other words, the elements that usually appear here seem to have taken the place. What? Okay, what's going on here? This is confusing to students. I still get questions in general chemistry classes. Which is correct? Okay, well, which is correct? Let's do the triads on it. If you do the usual one, yttrium, lanthanum, and actinium, you're nowhere near having a perfect triad. But if you do yttrium, lutetium, lawrencium, it's a perfect triad. Right? Now, you may say, well, I don't care about triads. Give me something else. Okay? Triads may be just numerology. Okay, here's something else. Consider the long form periodic table, which, as I was saying before, is the more correct version, because these elements do belong in the body of the table. And now try and put lanthanum and actinium there, and you get something very strange. If you follow through the elements, you get 71, 57, 72, 103, 89, 104. That's got to be wrong. Okay? If you do it the other way, perfectly okay. Right? So this does not rely on accepting my triads argument. This is just a natural consequence of going to the more correct long form table. So it's amazing to me that people are still wanting to do it in this way. Now, of course, when they do it in this way, they often do it in the medium long form table, where this effect is masked. There is actually a third possibility, which is to do it that way, where you do not interrupt the sequence of atomic numbers. But on the other hand, you're doing something rather nasty here. You're breaking up the D block into 2 very uneven portions. A group of one group here and then 9 groups here. That feels very uncomfortable to me. But strange things happen. You have to break up your transition, your D block. No other block is broken up like that, just the D block. So I'm coming to the end of this. Are atomic number triads just a form of numerology? Do they point to something deeper? If triads are really fundamental, we've got to give an explanation to them. And that hasn't happened yet. Right? Could it be that it's the nucleus that's directly governing electronic structure? Well, that would require new physics. Right? At the moment, we do not believe that the nucleus has any influence on how the electrons arrange themselves. There are a few very exotic effects where the nucleus is supposed to affect chemistry. Parity violation in certain atoms, the difference between right and left-handed amino acids may have its origin in the nucleus and beta decay and so on, but this is a long shot. On the other hand, isn't it just enough that the atomic number is equal to the number of electrons and that quantum mechanics gives the electronic structure? In other words, on this argument, there doesn't need to be a justification for triads. Triads concerns the number of electrons, which is equal to the number of protons. And the way the electrons arrange themselves is dictated by quantum mechanics. There are really 3 main forms of the periodic table. Right? There shouldn't be 1,000 of them. There's this form, the 8-column table, the classic Mendeleev form. There's the 18-column table, the one we're all familiar with. And then there's the long form table. That's really the issue. And I suggest to you that this is by far the more correct one, because every element is in its place, all the number sequences are continuous, there's no annoying footnote at the bottom. If you're interested, I have a whole lot of educational resources about the table and elements on my website. Thank you very much for your patience. And Please ask the question.